Good evening, everyone. Welcome to the second workshop of IEEEXtreme 18.0. Tonight, we are kicking off things with an exciting session on conquering complex problems, a step-by-step approach, with our esteemed speaker, Mr. Lakshit Nishankar, developer at labml.ai and fourth place winner of Extreme 17.0 in Sri Lanka. Today's session focuses on a step-by-step approach in conquering complex problems, where you'll gain insights into key problem-solving strategies and practical techniques that will enhance your ability to tackle challenging coding tasks with confidence. Now let's give a warm welcome to our speaker, Mr. Lakshit Nishankar, developer at labml.ai. He will be guiding us through today's workshop on conquering complex problems through a step-by-step approach. We are truly excited to have you with us and look forward to the valuable insights you'll be sharing. Over to you, sir.
Hi, hello everyone. Hope everyone can hear me and see me. Let me share my screen. You guys can see my screen, right?
Yes.
Okay, thank you. So welcome to the workshop. I think this is the second workshop. So let's get started. So first about me, I'm Lakshit Nishankar. I've been a competitive programmer for more than 5 years now. So my Git, if you want to reach me, my GitHub username is lakshit-43, and here's my email, lakshit.k.nishank@gmail.com. Or you can find me on LinkedIn or somewhere if you want to reach me. So here's the plan for today. So first we are going to go through how to read a statement, and then I'm going to talk a little bit about the environment setup when doing competitive programming. And then we'll go straight to the main part, the problem discussion. Okay, so I hope everyone's familiar with competitive programming. So IEEE Extreme is a competitive programming contest, and in competitive programming, there's like a formal way to present problems. So there will be a statement, and the statement has a couple of main parts. So first there's a problem statement, and then there is the input formats, output formats, and then constraints. And then there will be a sample test case description for you. And so let's go through each part. So first in the problem statement, there can be a backstory, like some story surrounding the problem. So usually it's a bit irrelevant to solve the problem. You don't really have to know the backstory, but the problem is sometimes that the backstory is kind of merged into the problem statement. So you can't separate that story and the problem statement. I've seen in some problems in competitions in code forces. So there will be a story and a problem statement separated. Like they say some backstory about some funny story about the problem, and then they put on a separate. And after that, there will be a formal problem statement. So the formal problem statement is enough to solve the problem, but the story is kind of optional. But most of the times, the story is kind of merged into the problem. So for example, here I had so let me read the problem. So here it says Alice has a bag of pebbles. She will eat the smallest pebble first, second smallest next, etc. She takes 1 second to eat a pebble. When can she eat a pebble of weight X? So the story around here is there's a person named Alice. She has a bag of pebbles, and she's gonna eat eat the pebbles in the ascending order. And then it takes a second to eat one pebble, and when can she reach the pebble of weight X? So there's a story here, but if there was a formal problem statement, it's just that given a list of numbers, find the index of X in the sorted list. So both of these are the same thing. there's a in the Alice example, there's a backstory, but in the second line, there's only like a formal problem statement that's enough to solve the problem. So something, okay, so the main statement is the part I mean here, this formal part, the part that's enough for us to solve a problem. So in some problems, you will get like a formal problem statement with mathematical definition and stuff like that. So you'll be lucky to have something like that, because you don't have to like go through the entire story. Like sometimes the stories are like a page long. So if you get like a formal statement, it's going to be easier for you. But something I personally noticed is that easy problems tend to have confusing statements with like stories. So the reason is if they provide the easy statement, like as in like some with mathematical definition, as it's going to be like pretty easy to solve the problem. So when the problem is easy, sometimes problem setters like make it confusing with the story. So it's going to be a little bit harder than it really is to solve the problem. Okay, so the next thing is input format. So the usual workflow of a competitive programming problem is there will be an input. That means they'll give you some test cases, and you have to write a program such that it takes those inputs, process it, gives some output in the given format. So taking inputs is a main part when solving programming problems. So there are a couple of main types of inputs. So we have integers, floats, and character strings. So usually these, like in lots of problems, you will have to get like a list of inputs. So sometimes the list like if there's a list of integers in the input, sometimes these are space separated, sometimes these are new line separated. So like there's a single value in a single line. So if you're using C++, you will probably use C to take inputs. So when using that, it doesn't really care if the delimiter is space or new line. It just divides the inputs with white space. So this list being separated with spaces on new lines thing does not matter when taking inputs with C. So another thing to consider is when even in like Python, there are like standard methods to get inputs of strings, integers, stuff like that. So most of these inputs are like white space separated, but if there's like an input string, and if the problem statement states that there can be like white space characters inside the input string, you'll have to take care of that. So you're going to have to take the input like in C++, there's a getLine function to get the input of the entire line. And there has to be something for Python too. So you have to like focus about that too. So sometimes when you get a list of integers, like, yeah, so when you get a list, sometimes before the list, you get an integer saying how many items are in the list. So in modern problems, I'm seeing less of that. So I think the main reason is maybe people used to see when doing computer programming in early days, and I think it's a really hard to like check the length of the input stream, and so getting how many elements are there in the list beforehand is gonna make it really easier for you to write a solution. So, but in modern programming languages, like it's not really that hard. You can, like in Python, for an example, you can take the entire line as input and then like separate it with space and then like count how many items are in the list. So these are the usual input formats. And then another thing. So there are some problems where you'll get multiple test cases. So here what I mean is like in a single run of your program, you will have to solve multiple instances of that problem. So usually the input format is, for an example, if the problem has to take 2 integers, so the input format is going to be, first there will be a single integer saying how many test cases are there, and then after that you have to for an example, if the number of test cases are t, you have to loop through it t times, taking 2 inputs each for each test case. So the thing I wanted to mention here is since these test cases are like does not depend on each other, they are like they're like the multiple instances of the same problem, but the output of one test case does not affect the other test cases. So when taking inputs, what you can do is like first get the logic of taking inputs of a single test case into a separate function, and then in the main entry point of your program, take the number of test cases, loop through it, move to that function to solve a single test case, and forget about this. So if you like use a loop to loop through test cases, and inside that loop you're going to solve everything there, it's going to be like a little bit messy, since we know that those test cases are does not depend on each other. Like you can write something like this on the entry point and then forget about it. And then output format. So the main concerns in the output format is sometimes some problems like here, for an example, for a test case, if you have the output 5, sometimes the problem statement requires you to output it like this. Okay, so like this. So an example contest is Meta Hacker Cup. In Meta Hacker Cup, you have to use a formatting like this. There's not a common format in IEEE as far as I remember, but there can be like some specific problems with the format. So in cases like this, what you can do is you can write some function to do the formatting for you. So you don't have to like write this test case #1 everywhere you need to output something. So another thing is precision. So in the problems where like the floating point arithmetic is used, since I think you know that computers can't really do floating point arithmetic like accurately. For an example, the decimal 0.1, you can't really represent that in binary. So if you do represent it in binary, there will be some little bit of error. So usually if a problem has these floating point numbers, they will ignore some like error. So they will ask you to like print whatever your answer to like 6 decimal point, stuff like that. So in that case, you need to know in whatever programming language you are using, you have to know how to format these numbers into the given decimal points. So this 6 decimal point is a really common precision, I think, from what I've seen. Okay, so another thing we have to focus is interactive problems. So I said earlier that the usual way of computer programming is like there are some test cases. You write a program to take those as input, and then you output something. So there are a problem type called interactive problems. In the last day, they went in interactive problems. I'm not sure if there will be any in this year, but you have to be ready in case those appear. So interactive problems is, so the input, the input of your program depends on like intermediate outputs of your own program. So it's like there will be a single input first, and then you have to output something, then it will input something, you have to output something again. Like there will be a cycle like that. Then there will be like multiple steps of input and output before like ending your program. So something you have to focus here is, for an example, in C++, you have to, when you take an input and output something, you have to do this thing called flushing the output stream. If you don't flush the output stream, your program can't read the next input. So sometimes I think this has happened to me when I was starting out. So I take input, I output something, and then I like the site is supposed to send me another input, but my code is waiting for something to come, and there will be a time limit exceeded exception. So for the reason for that is I have to flush the output stream after outputting something. So maybe just, I'm not sure what programming language you are using, and you will need to use, I don't know whether you will need to use it. So maybe like just read about it a bit, and you won't get stuck in an actual contest. Okay. Constraints. So constraints are our main problem. So when you're solving a problem, there will be some like some hardware constraints, like you will get 256 MB of memory, you will get 2 seconds of runtime, stuff like that. Like the most important part of that is runtime. So I'll first talk about the runtime. So in runtime, usually problems will have like a second or two of runtime. In some contest, I don't remember. Some Google competitions, I think, had like 10 seconds of runtime. But the usual amount is like a second, 2 or 3, if the problems takes long to solve. So, and I'm gonna assume you all know about time complexity. So again, time complexity, you have to like focus a lot on time complexity. I think that like this is like the main bottleneck of solving problems, because if you had infinite time, you can solve any problem. So yeah. So in time complexity, so basically, if you don't know about time complexity, that means the amount of operations a program gonna run depending on the input size. So for an example, if there's like a single for loop, like if you input something and what your program is doing is like doing a single loop that given number times, that means time complexity is n. So if there's like a nested loop doing first loop doing n steps, second loop doing n steps, then there will be like total n squared steps. So the time complexity is n squared. And another thing is different computers take different times to like in terms of milliseconds, let's say, different computers take different times to run operations. So we can't really like look at a program and like very accurately say how long this program gonna run. So we are only concerned about like an approximate figure. So for an average, it's like safe to assume that a normal computer can run 10 to the power 8 operations in a second. So that's like the baseline we are going for. So we are going to do all our calculations around that, like just to get an idea. So if a problem statement has an input n and it's 10 to the power 3, so like 1000. So the problem statement gives you a list of numbers, you need to do something about it. And if the size of that array is 10 to the power 3, 1000, the length is 1000. So it's safe to assume that they are expecting a n squared solution, because n squared is 10 to the power 6. 10 to the power 6 is less than 10 to the power 8. So you can safely run that in a second. So like I said, every different computers take different times to run operations. So there's like a wiggle room here already. So therefore, we are not really concerned about like the exact number of operations either. We need just like a very rough figure. So if like I said, if there are like 2 nested loops with n steps each, and there are multiple things happening inside, like if those are like constant times, like addition, subtraction, stuff like that, you can just ignore those. Then you can just say the runtime is n squared. So I'm just teaching you like a very rough idea of time complexity. So because to do computer programming, we just need like a rough idea. We don't need any specific like asymptotic function, stuff like that. So if the input size, so in the last example, I said if the you get a list of numbers, you have to do something about it and output something. If the input size is 10 to the power 3, you can do an n squared. If the input size is 10 to the power 6, you can do a n log n. So here, whenever I say log, I mean log base 2. Related to computer science, I think whenever you see log, it's safe to assume that they mean log base 2. So log base 2 is like a really common thing when doing these problems. Like lots of data structures have time complexity in the order of log n, like segment tree, stuff like that. So these n log n, n squared, n log n, n square root n, these stuff are like very common time complexities when solving problems. So if the input size is 10 to the power 6, that means length is million. They may be accepting a solution with n log n complexity. If the input size is like 10 to the power 7, they are probably expecting a linear time solution. So linear is just n. So n squared means quadratic, n cube means cube. So n we call n linear. So another thing is like reading inputs is also a bottleneck. So you may be wondering why I haven't added like 10 to the power 8 inputs for a second. The reason is, I think to read 10 to the power 8 inputs, it's gonna take a little bit longer than a second. So, and if the input size is like 10 to the power 5, maybe they're expecting a n square root 10 solution. Square root 10 is also a little bit common, I think, in there's this thing called square root decomposition. Square root 10 is also common in data structures and some algorithms. So what I'm trying to say here is, given the input size, and like the time allowed for the problem, you can like estimate what kind of complexity the solution needs to have. So based on that, you can try to think about a solution. So for an example, if there's a list of integers with like a size of 100, and then when you read the problem and you think maybe I can do something like I can sort this and do a binary search, something like that, and get an answer. But if since the input size is n squared, input size is 1000, you can easily do an n squared solution. So you don't have to like improve it much further than that. Like, you probably won't need a binary search with n log n complexity because you're allowed to do n squared. So yeah. Also, another tip for you. So we are not like used to do calculations with the log base 2, right? So I'm going to show you a trick on how to do this. So if you want to get the log of something, so input sizes are usually in the order of 10 to the power. So input size is going to be 10 to the power 1, 2, 3, 4, 5, 6, something like that. So 2 to the power 3 is 8. So 2 to the power 3 is approximately equals to 10. So in that case, wait, let me get on the whiteboard. Where's my mouse? Can you guys still see my screen? I changed the tab. Can someone like raise your hand or something? Wait, okay, thanks. So 2 to the power 3 approximately equals to 10. If you wanted to find the log base 2 of 100, now let's say 1000. This is log. Yeah, I'm drawing with my mouse. 10 to the power 3. That means log 10 equals 2 to the power 3 into 3. This means 9, right? So we can get 9 here. Then with those log rules, we can get 9 here. And then log 2 to the base 2 is 2. Then the answer is 9. So from what I did, log 1000 is, log base 2000 is 9. Wait, let me check the answer. Yeah, log base 2000 is 9.966. So it was like roughly same. So when dealing with time complexity, we are only concerned about like rough figures. So if you need to do a quick calculation in your head, like this is enough. Yeah, okay. Oh, by the way, I forgot to tell you, I think there's a question link in the meeting. If you have any questions, you can maybe raise your hand or send that in the question link or drop a text. Not drop a text, maybe I don't know where I can see text. And I found it, I think. No, not yet. Why does the input size matter? Okay, we got a question. So, let me think of an example. Okay, let's say I'm thinking of a sample problem. Okay, simple now. So the problem is like this. There's a list of integers with length n, and there will be q queries. In each query, the problem gives you another integer and asks if that integer is available in that given list. So let me go back to the whiteboard. Yeah, okay. So the problem statement is there's a list of integers, the length of that is n, and there will be q queries. For each query, the problem statement will give you a single integer. What you have to do is you have to output yes or no based on whether that integer is available on the first given list. So the reason for input size is, let's say, okay, so n is 10 to 3 and q is 10 to 4. So the obvious solution for this problem is, for each query, you are going to go through the entire list of integers and then output whether you found it or not. So for that, the time complexity will be, so there will be q queries. Let's imagine the worst case. In the worst case, the integer you're looking for is available at the end of the list, or maybe it's not available at all. So in that case, you have to like go through the entire list in every single query. So there are 10 to the power 4 queries. So the list of integers is 10 to the power 3. So you are going to do 10 to the power 3 checks. No, this is small. Let's do 10 to the power 5. Okay. So there are 10 to the power 5 integers. So in every single check, you will have to like compare 10 to the power 5 integers, and then you have to do that 10 to the power 4 times. So this will be 10 to the power 9. 10 to the power 9 means 10 into 10 to 8 now. So we said like a computer can do like 10 to the power 8 operations in a second. So this solution takes like 10 seconds to run. If you were to do like a binary search, I won't go in details about doing the binary search. So what you can do is you can first sort this list of numbers with n log n complexity. That is 10 to the power 5 into log 10 to the power 5. Maybe it's going to be like 10 to the power 6. So after that, then after that, you can do each query in log n time. 10 to the power 5 log n means 10 to the power 5 means 2 to the power 3 into 5, 20. So each query will take only 20 operations. So 10 to the power 4 into 20, 2 into 10 to the power 5. Our new solution is 2 into 10 to the power 5. So this takes like a lot less than a second. So I think it's pretty clear that based on the input size, the solution we need changes. When the input size increases, we have to further optimize our solution to match the given runtime. So that's why the input size matters. Is that answer clear? Okay, I hope it's clear. Wait, let in the chat. If there's anything else, just ask again. Okay, I'll go back to the presentation. So, okay, another thing. So, in subproblems, mostly in problems about like, like permutations and combinatorics, like in combinatorics problems tend to have like, in the equation for permutations, there's a term with n factorial. So in factorials are really, really big numbers. So like you won't be able to like 100 factorial, you won't be able to store it in like any 64-bit integer or something. So in problems like that, the usually problem statement will ask you to mod your answer by usually 10 to the 9 plus 7. This 10 to the 9 plus 7 is a prime, I think, or any other prime number. So basically what they are asking is like find the answer and mod that answer by 10 to the power 9 plus 7. And then, so modding means like dividing and getting the remainder. So the answer for this is always going to be less than 10 to the power 9 plus 7. So output that number. So, oh, and also if you are going to participate in IEEE Extreme, first go through some modular arithmetic, like how do you perform multiplication and then division under mod. So yeah. So in cases where you have to mod your answer by 10 to the power 9 plus 7, so 32-bit integers can store, I think, integers up to like 2 billion, like that means 2 and 10 to the power 9. So it should be able to store answers in this range, right? But I think in programming language like Python, this doesn't matter because there are no like 32-bit, 60-bit, something like they can get as big as like any amount you want. But if you're using like any other programming language with like static types, you have to like maybe use either 32-bit integers or 62-bit, 64-bit integers, especially if you're using C++. So what I'm asking here is, even though this can even though a 32-bit integer can store answers in this range, it's better to use 64-bit integers. The reason is in an intermediate step of like doing multiplication, there can be an integer overflow. That means you'll be trying to store something bigger than 2 billion in a 32-bit integer, and it will overflow into negative side, and the whole calculation becomes a mess. So if you have to deal with large integers, like it's better to use the largest integer type you can use. Okay. Another thing is, input sizes like 10 to the power 5, 10 to the power 7, 10 to the power 3, like those are pretty common. And usually for integers, like if there's a list of integers and even if the solution does not depend on that like size of integer, for an example, if you get a list of integers and the task you have to do is sort them, like the integer range like does not matter, right? The input size only matters. So usually they will be like they will put in constraint saying that these integers are less than 10 to the power 9. The reason is 10 to the power 9 is like the safe limit in 32-bit integers. So if some problems have like 10 to the power 18, like the limit, the usual limit is 10 to the power 9, but in this problem limit is 10 to the power 18. So if there's something like that, maybe the solution to this problem is somehow related to that, because that's an odd constraint. Like there's no reason to add that. So, and if there is like very small concerns like 10, like 10, 25, something like that. So that's very odd too. So maybe you have to like focus on that when thinking about your solution. So this small constants thing does not really matter in like very easy problems, because in like very easy problems, they provide like very small constant for like for everyone to write solution. So if the problem statement is like very easy, you can ignore these odd constant. If not, and if you're thinking about solution and you are stuck, maybe think about why these odd constraints matter. Okay, so now we come to the environment setup. So let's talk about programming languages. So from my personal opinion, there are only like these two languages to try competitive programming, like C++, Python. You can use other languages, like IEEE Extreme allows lots of languages, but I think these two languages can cover all use cases. So I personally like programming with C++, but sometimes I use Python when it's easier. We'll talk about that in our first problem. So the main reason I use C++ is, so I started my computer programming with Olympiads. So in Olympiad, when I first participated, so informatics Olympiad is also a competitive programming competition for high school students. So they only allowed Java and C++, and then they ditched the support for Java. They only allow C++. So that's the main reason I started C++. But they are not going to allow Python, because Python is really slow compared to C++. So they can't like set time limits for problems for both languages. So the reason I keep using C++ is it's really fast. That's like the only reason. Oh, and in when thinking about resources on the internet, like I think like more than 90% of competitive programming resources are based on C++. Yeah, and the next language is Python. Sometimes I use Python too. I think lots of people who are getting into competitive programming uses Python too. The reason is I don't use Python always because it's slow. So when I do use it, it's because like it's pretty easier than C++. Like there are some standard functions to do some stuff in C++ which you don't. So this is going to get clear when doing the first problem discussion too. Okay, so the next couple of slides are based on C++, but like it does relate to other languages too. Okay, so templates. In most of the contests, like I think most of the contests are online, even in on-site contests. In some contests, they allow some like a 10-minute time frame before the start of the contest for you to write any boilerplate code if you want. So I think it's better to start using a template. Lots of competitive programming problems have very common stuff. For an example, this test cases thing. So if the entire contest has problems with these test cases, in every single problem, you will have to take the input T, loop through it, write another function, this boilerplate. So what you can do is you can like make a template and then copy paste it whenever you want to solve a problem. And another thing is like when you have to output something in like a predefined format. So this is I made this for Meta Hacker Cup. So in every problem of Meta Hacker Cup, I have to output the solutions in this format. So instead of writing it again and again, I added this to my template. So I can use this in when solving every problem. And this is very specific to C++. So if you're using C++, and let's say you're using it because you need to make your code run faster, then this couple of lines, like these 3 lines, will make your code a lot faster. So in default, when taking inputs and outputs in C++, they are doing this syncing thing with the input-output streams. So except in interactive problems, when doing a normal computer programming problem, usually at the start you can take all the inputs and then output everything. So in that case, you don't have to really sync your inputs and outputs. So you can just turn that off and it will make your code like run much faster. This is like a trick specific for C++ programmers. Oh, and another thing is uh, there will be lots of problems with related to grids in IEEE-Extreme. So like in a grid, let's say you are in some coordinate and you have to visit your neighbors. So here neighbors means your top, down, left and right. So moving those coordinates to your neighbors means, for an example, moving to top means you have to increment your y-axis by 1 and then uh, keep the x-axis as it is. Then going left means incrementing x once and keeping y as it is. So stuff like that. So here this I wrote this boilerplate so I can like do a single loop, and here x hat and y hat means the coordinates of my neighbors. So from a given coordinate x and y, I can iterate to all the neighbors in a single loop without like much hassle. So like if you're not familiar with this, when I'm explaining this to you, like it can be like sound a little bit tricky. Even in programming, that's the case. So having something like this will help you a lot. I think there were like 2 grid problems in last IEEE Extreme, if I remember correctly. So I'll share these slides after this. So like take a look and see for yourself why this is useful. Uh, this is also something specific to C++ programmers. So here what I'm doing is when I'm running my code locally, I'm replacing my input stream with the input text file and output stream with an output text file. So I don't have to deal with terminals all the time. So I'll open 2 files, input and output. Then I copy all input in the input file. Then when I run the code, the output will be in the output file. So it makes my life so much easier. So if you're a C++ programmer, you can use this. In case someone wanted my C++ like compiler commands, I added it here. If you're a C++ programmer, like you can use it. I'll share this later. Okay, so that's everything like theory stuff I planned. So we can start solving problems now. So the first we have yeah. So the first problem I picked is Caesar redux. This was in last IEEE Extreme. This is the link if you want to open now. So wait, give me a minute. Yeah, sorry about that. I'm back. So before we move on to the problem discussion, does anyone have any problems with what I've done so far? I think no. If you do have problems, just send that in that Q&A. Okay. Okay, so the first problem is Caesar redux. So this is probably the easiest problem in the last extreme. Okay, so this is the problem statement. I'll go through it. The Caesar cipher is a simple encryption technique that was used by Julius Caesar to send secret messages to his allies. It works by shifting the letters in the plain text message by a certain number of positions. Decryption is performed by shifting in the opposite direction by the same number of positions. A program that implements this technique is needed to encrypt plain text messages or decrypt a ciphertext message. Spaces are not affected by encryption or decryption. You need to determine whether the value set is provided in plain text or ciphertext. If the value provided is plain text, you should output the encrypted message given the shift value above. If the provided is decrypted message. Okay. So they say, so I think you heard about Caesar cipher. That means like shifting the characters in the alphabet. So for an example, if the shift is 3, no, shift is 1. If the input character is A, you have to shift it 1 and the encrypted character will be B. So yeah, so that's how this encryption thing works. You have to write a program to encrypt some messages like by shifting, and they say the decryption works by like de-shifting, like so negative shifting. So you have to your program should do both encryption and decryption. So here's the input format, standard input. Input begins with an integer n on a line by itself that indicates how many messages are in the input. The next two n lines contain a line with the shift amount followed by a line with either plain text or ciphertext message. Okay, so here, this is an example for those test cases I mentioned. So there are n test cases here. The output of one test case does not affect others. So in each test case, there will be two lines. The first line will contain the shift and the second line will contain a string. So here another thing to focus is this input string can contain spaces. So when taking the input, you will have to take the entire line as an input. Okay, so output. For each message in the output the plain text if the message is ciphertext, or the ciphertext if the message is plain text. Okay, so if we get a plain text message, we have to encrypt it. If we get a ciphertext message, we have to decrypt it and then print it. That's the output. So the constraint, n, the number of test cases will be less than 25. So here 25 is an odd constraint, but we don't really have to focus on that because this is a really, really easy problem. So in really easy problems like these or small constraints, it does not really matter. So the shift value will be between 1 and 25 including. Makes sense because there are like 26 letters in the alphabet. And each message will consist of lowercase letters and spaces and contain between 3 and 300 characters. Okay, they will only contain lowercase letters and spaces. If the message provided contains the word the, then it's plain text, otherwise it is ciphertext. Okay, pretty clear so far. Oh, yeah, no, I wasn't supposed to show that. So let's go to the problem. Okay. So this is how I'm going to solve it. I'm going to use Python to solve this. The reason is for this input string, there are spaces, so I have to like get the entire line, and it doesn't really say how long that this input is. And then another thing is to decide whether an input string is encrypted or not, we have to check whether that string has the word the on it. So if I were to do that in Python, let me just go through the code first. So this is the code we used in our IEEE Extreme like last year. So I didn't write this code, that's why this is in Python. And that's why the test case handling is inside a loop. If I were to do that, I'll like write a separate function to solve a single test case and like keep this looping through test cases separately. But for this, they are going to loop through the test cases and solve the problem in the loop body. So first what we are doing is we are taking the shift. Every test case has a shift input. So we are going to take the shift. And then we are going to take the entire line as an input. This is the ciphertext. We have to like, not a ciphertext, like could have used better variable naming. We have to either encrypt or decrypt it. So then we are going to split it. By default, the split will split by spaces. So then we have the ciphertext. In this ciphertext variable, we have like a list of words. And then I'm going to check if the word the is in this list. If I do find that, that means this is a normal string, we have to encrypt it. Otherwise, we have to decrypt it. So if I were to do this in C++, it's going to be a really, really pain because first we'll have to split the string and get it to a vector, and it's pretty hard already. Like we have to use a string stream or something, and then we'll have to go through each word checking if those strings match with the, or else we can maybe figure something out with regular expressions. We can probably do a one-liner with regular expressions, but in Python, as you can see, like this is pretty straightforward and like pretty easy to do. So here, we reach here means we'll have to encrypt our text. So what I'm going to do is I'm going to loop through every words in the input, and for every word, I'm going to get this ORD function returns, I think, the Unicode of that character. I think ASCII. So for letter A, we'll get like 97, I think. So we are going to get those characters. And then what we are going to do is first, we are going to subtract it by 97 to make it like start from 0. So for if we subtract 97 from each character ASCII, then for A we'll get 0, for B we'll get 1, for C we'll get 2, like so on and so forth. So after that, I'm going to like I have to shift this. So I'm going to reduce this by the amount shift, and then whatever I do with this shift, that has to be in the range between 0 and 26, because there are only 26 characters in the alphabet. So in the Caesar cipher, if you shift y by 2 to the right, then y becomes z, then after that z becomes a. So it's like circular. So implement the circular behavior, we need to mod this by 26. So we are going to divide this by 26 and get the remainder. So if you think about it, it implements this circular behavior. Then after that, so after all this, we'll have an encrypted index between 0 and 26. So I'll have to turn that back again into characters. So I'm going to again add 97 to it. So if this was A, this going to be, this highlighted part going to be 0. And if I add 97 to it, the result is 97. If I convert 97 into a character, the converted character will be A. So I do that. Then I can convert those every indices to characters. And then I'm going to, now I have a list, so I'm going to join that list to make a string, and I'm going to append that word into our sentence list. Then after that, I'm going to like put together this sentence with spaces and then print it. So if I were to decrypt it, I'm going to do the same thing. Instead of doing the O minus shift, I'm going to O plus shift, because I have to move it to the right. So everything else is same. I'm going to do the same thing, like modding by 26 plus 97, everything. And then I'm going to print the sentence. So this is pretty straightforward. Like the problem statement give us something to do, and we basically did it. Like there wasn't much thinking. So I submitted it. If I want to submit, yeah, it takes hundreds. Okay, so we solved a single problems. We got like 100 marks. Yeah, 100 marks. Does anybody have any questions? We have 3 more questions. So if you don't have questions, I'll move on to the next one. If you do, doesn't matter if I'm discussing something else, just ask. Okay, can you show us how your code works? How do I show how my code works? Can you be more specific? Like, do I have to go through what's happening, or do I need to run some print somewhere and like show you the middle steps? Mhm. I don't know how it encrypts and decrypts the input. Okay. Okay, so what's happening here is, let's say the entire input string is B. So this is like the entire string. So to encrypt it, I don't remember if you have to shift left or right. I think for this, let's say for encrypting, you have to like shift to the right by 5. So shift is 5. So if I were to encrypt this, so if I were to encrypt this, this says 5. So what I have to do is I'm going to use a text box here. So first letter is A, B, C, D, E, F. 1, 2, 3. So shifting by 5 means I'm going to make B shift by 1 to C, another to D, E, F, G. If I shift by 5 times, I'm going to get G. So B will become G. So this is what should be happening, right? So I think your problem is like, how did I implement this? So what I did was, first, so every character, like when programming, every character is represented by their Unicode character. So for letter A, the numerical representation of A is 97. You can like refer to an ASCII table and see like letter A is 97. So by that ORDA function, we get that for a given character, we can get the 97 or whatever numerical representation is. So if we were to get the numerical representation and subtract 97 from it, we'll get an index of our character in the alphabet. For an example, for C, we'll get 100. But wait, 97, 98, no, wait. For C, we'll get 99. If I were to subtract 97 by it, I'll get 2. So 2 means this is 0 indexed. So 2 means like the third character in the alphabet, which is C. So by getting the numerical representation and subtracting 97 for each character, we are going to get an index of that character in the alphabet. So that part is clear. So now we have an index for every character. So now what we are going to do is we are going to shift this. So for an example, for this example, the numerical representation of B is has to be 98. I subtract 97 by it and then I get 1. So the index of B is 1. Then after that, shifting by 5 means I'm going to add 5 to it. Then after that, I'll get 6. So then we got that index by like subtracting 97 from the numerical representation. So what I'm going to do is I'm going to add 97 back to get that Unicode representation. So we get this 6. This is the shifted value because I added 5. I'm going to add 97 to it. 6 plus 97 is 103. If I convert 103 to ASCII, that should be G. Wait, let me check. Yeah. 103, if I convert 103 into a character by the Python, I think the function name is CHR. So if I convert this integer to a character using that function, it's going to be G. So here's what's happening for each character in the input string. I'm going to get a Unicode number. Then from that, I'm going to subtract 97 and then I get an index in the alphabet. Then after that, I'm going to add whatever the shift we want to it. And then after that, I'm going to convert it back to a character and get the encoded value by that shifting. So yeah, that's what's happening here. So we are going to get that number and then we are subtracting 97. Then we are doing the shift thing. In this case, we had to like subtract the shift, not add to it. And then after that, I'm going to add 97 back to get that Unicode number. And then in the next line, I'm going to make a character out of it. So it's going to be a shifted character. So is that clear? And I have another question. How much time do you get to do a question like this? If I remember correctly, there's not like a specific time for a question. I'm not sure about this, but I think you get like the questions disappeared. Okay, so I think at the start of the competition you get 3 questions, and for each hour you get another. So I don't know, maybe hour for a problem. There's something like that. It can be more than that, or it can be less than that. There's no like specific time. You can use like entire 24 hours to solve this problem or something. Yep. Do we have another problem? Yeah, okay. Since we don't have much time left, I'm going to move on to the next question. Yeah. Yeah, okay, so for this problem I like added screenshots of parts, but I'm too bored to do the same thing for next problem, so we're not gonna do that. So the next problem is war games. I think this is like this is also a relatively easy problem. This is the link. Oh, the link is wrong. Wait. What? Yeah, that's the link. Okay, so I'm not sure if you okay. So this problem has a 1 second time limit and 256 MB of memory limit, pretty standard. Let's go through the problem statement. In one variant of the game of war, two players are dealt a pile of playing cards. I don't know any variant of game of war. So at each turn, both players turn over their top card and the player with the higher card adds the lower card to the bottom of their deck. Okay, so two players have two card decks, and then at each turns, both players turn over their top card, and after that, the player with the higher card adds the lower card to the bottom of the deck. Okay, so the player with the higher card is going to get the card of the other person and then get it into his deck at the bottom. The higher card is then discarded. Okay. If the cards that are turned over have the same values, both players return their card to the bottom of their pile. Okay. The player that runs out of cards loses the game. If no player will run out of cards, the game ends in a draw. Your challenge is to determine which player will win a game given the cards in each player's pile. Okay, let's go through the input. Input begins with an integer n on line by itself that indicates how many games are in the input. Okay, so there are multiple games here. So this is like multiple test cases problem too. So the next two n lines describe the n games. With the first line in pair giving player one's card and the second line giving player two's card. The cards are listed from the top of the pile to the bottom of the pile and are described by single character 2, 3, 4, 5. Okay, so this is like a standard card deck. 2 to 9. If it was 10, there's 10, right? Okay, this doesn't have any 10. So, 10 is T. Okay, so Joker, Queen, King, Ace. So standard output is for each game, we have to output whether player 1 wins, player 2 wins, or a draw. And the constraints are the input size is 20, less than 25. Again, this is an easy problem, so it's not like really important. So each player will have between 1 and 51 cards, the standard deck. So the player may start with a different number of cards. The total number of cards both players will be less than or equal to 52. Okay, there is no restriction of the number of the game may include 52 cards with the value of a. Okay, there can be repetitions. So then let's go through the sample inputs. We have a single sample input. Okay, so in the first test case, first player has king 10-3, the second player has 2J 5J. In the first game, after the okay, so in the top there will be K and 2. So both players will turn over K and 2. when that the player, so the k has the higher value. Therefore, the second player has to first player will have to put the lower card into his deck, right? Yeah, player one adds the 2 to the end of their pile. Yeah. Then after that, k will be discarded. So the first player have t3 2, and second player have j5 again j. So after that, then there's t and j on the top, and since j is higher, j will be discarded, t will be added to this, and the first player will have 3 2, and the second player will have 5 j2. So it's pretty clear, I think, and then this happens for a while, and then after that they say player one will win. Yeah. Okay, so now we'll have to think about the solution. So this seems like an easy problem, and the constraints are like a lot small. So maybe a naive approach will work. And then at each step, the value of the higher card will discarded, and then the lower card is added to the player with the higher card. So at each step, like if you take the total of their cards at each step, unless their values are similar, the total number of cards will be reduced by 1. If the top values of their both players cards are similar, then nothing's gonna change. But it can't happen always. If it were to happen always, it's gonna be a draw because nothing's gonna change. So or else at each step, like there will be one less card in each step. So here's how I would try to solve this problem. So what I'm going to do is, it's a pretty basic thing, right? Like if we were to keep 2 lists of card, and then like we can like simulate this problem, like we are gonna check the topmost cards, and then like who's bigger, and then after that doing like if it were a draw, we are going to put both of them in their cards back again. If there's a difference, we are going to discard the high one in get the low one here and add the next list. Like the simulation part is like a pretty straightforward. So what I can do is I can do the simulation, but the problem is I don't know how long will this run. Okay, let's assume there are no draws. If there are no draws, like if there are no 2 cards with the same value, at every single step, they are going to be one less card. So since they have like 52 cards in 52 steps, this game has to be over. But if there were cards with same value, they are gonna add back again into their list. So if we were to simulate it, somewhere we find 2 cards with the same value, we are going to put them in back of the list, and then we keep doing that again and again and again. And then if we meet those 2 cards again, that means they are gonna get add back to the list. We are going to meet them again, add back to the list. We are going to meet them again. So there's no point going forward because it's going to be a draw. We can't like remove both those cards. So I know that it's straightforward to implement this problem. The issue is I don't know how long will I have to keep on looping. But at each non-draw step, the total number of cards will be reduced by 1 at each draw step, like with the, if both cards have the same value, the total number of cards not gonna change, but I'm going to like put a soft limit there saying these draws can happen only like 52 times. Like let's say 50, like 50 times. If they were, since the card deck have like 50 cards, if the draws were to happen more than 50 times, that means like all the cards are draws, so the game will definitely end in a draw. So what I'm going to do is I'm going to run this loop like 100 times. In 100 times, if I get a winning player, I'm going to say he won the game. If I don't get a winning player, I'm going to assume that this is going to run forever. So that's my thinking process. Does anyone have any issues about that? I can show the code. Yeah, if someone has any problems, they can ask me. Until then, I'll share my problems solution. So I wrote a helper function to, so this is C++ because I wrote this. So I wrote a helper function to get the card value. If the character is greater than 2 and less than 9, that means it's one of these. I'm going to get the value of it like straight away. And if the value card character is T, I'm going to return 10. If it's J, I'm going to return 11, for 12 for Q, 13 for K, 14 for S. So this function, whenever I input a character, it will give me like the numerical value of it. So here, this is that input thing I explained about C++. So I'm going to get the input, the amount of inputs, and then like number of test cases. I'm going to run the code for that all test cases. For each test case. So in Python, this part will be a much shorter and easier, but in C++, what I have to do is I have to do the take the input of a line here, and then I'm going to create a string stream to like divided by white space. So in Python, you would do something like we did in the last problems, like take the input divided by space, like split it. So that's what I'm doing here. I'm going to split it by spaces and adding it to this vector. I'm going to do it for both of their card decks. And then what I'm doing here is I'm simulating this for 100 steps. So after 100 steps, if I get a winner, I'm going to output him as the winner. If I don't get a winner, I'm going to output as draw. So here implementation is a little bit of complex. I think you can do a much sort of thing in Python. So what I'm going to do here is I'm going to keep a vector. Vector means like a dynamically sized array. So I can append characters to it like at the end in constant time. But for removing, it takes linear time. But for here, I'm going to do is I'm going to wait, no, okay. So I'm gonna keep both of my card decks as, yeah, I can't draw straight. I'm going to keep both my card decks as okay. So after this, I'm going to keep a pointer to the start of this and start of this. So at each step, what I'm going to do is I'm going to check the topmost values. Then if this is a draw, I'm going to append this value here, append this value here, and move this pointer to here. And move this pointer to here. So like I can forget about this and I'm going to assume that this is the starting position of this array. So then I am going to check this this value and this value. So for an example, let's say this value is larger than this value. So I'm going to discard this. So that means I'm going to put this pointer here. So for like this vector starts from here. So for this, I'm going to remove these two. That means I'm going to move my pointer here. And for this value, I'm going to append here. So this is how the simulation works. And then if there's a point where I have this many elements and my starting pointer is also here, that means like if my starting position is also the end, that means the vector is finished because I am assuming that all those elements left the pointer is removed. So if I ever reach that, like if my starting pointer ever reach the end of the vector, that means that vector is empty. So if I go back to the code again, yeah, so these are the starting pointers of string A and B, like first player and second player. So I'm keeping this to like how many times I'm running this. So this can also be a for loop. So I'm doing this 100 times. So if the first string is empty, that means my starting point is also the size of the vector. That means player 2 wins or else player 1 wins. If not, I'm going to like compare the starting cards on both decks. If it's similar, I'm going to add those back again to both those lists and move my starting point to one to the right. And if not, I'm going to do the comparison and do the appropriate thing and move my pointers next. So this is like a basic simulation. I'm like directly simulating what I'm told to do in the problem statement. So the important observation here is this is gonna end in like pretty small number of steps. For an in this example, it's gonna end in 100 steps if I were to submit it. Okay, yeah, it works. So this is how I would solve this war games problems. Does anyone have any problems? So there's a problem question. Will attending the event without any actual knowledge of programming cause a problem since I've just started learning and intend to learn from this event? I'm assuming you're referring to IEEE Extreme. If so, like yeah, there's no harm in participating. Like maybe you can do some like get some easy problem scores with ChatGPT or with the help of ChatGPT or something. Like there's no harm in doing IEEE Extreme. Like you can always try and try again. Like there's no harm. I think you should definitely try. It will be a valuable experience. Are there any more problems? Yeah, okay, so I prepared 2 more problems to discuss, but they will probably take much longer than this because they are a little bit harder. One problem is like a graph problem with topological sort, and the other problem is a dynamic programming one. Okay, so someone asked what is dynamic programming. So dynamic programming is like a problem solving technique, like it's really popular, and you probably will get like couple of problems, like at least 2-3 problems in the IEEE extreme related to dynamic programming. So dynamic programming basically means like dividing a problem into sub problems, and then like if there are repeated sub problems, you are going to ignore some and only use unique sub problems, and with those solving those sub problems, you're going to get the answer of the main problem. So it's like a big topic to discuss here, and I don't think I have time. So the other 2 problems I prepared is this watershed problem. So yeah, I don't think I have time to go through all this, but maybe I can share the solutions with you, and if there are any problems with if you encounter any problem with IEEE extreme problems, like reach out to me and I'll help you as much as I can. So yeah. Mm, and someone asked how many questions are in IEEE extreme. I don't remember. I think like 20, at least 24, because it's a 24-hour competition. Yeah. So yeah. So I think you learned something today. Since I don't have time to explain the last 2 problems, I'm gonna stop here. If you have any questions, you can ask me.
Thank you, Mr. Lakshit, for sharing your expertise and guiding us. We would like to take a moment to express our heartfelt gratitude to our speaker, Mr. Lakshit Nishankar, with a token of appreciation. Your time and effort in leading our IEEE Extreme Workshop 2 on conquering complex problems, a step-by-step approach, is greatly appreciated. Thank you for sharing your invaluable knowledge and expertise with us.